Ready?
Ready.
So, good afternoon, everybody. It's the final afternoon of the conference. Congratulations to all of you who made it this far. Another 3 talks, and you're free to come and drink with us again. So this is the final session of junior talks, where junior is, I mean, a bit stretched, but still junior compared to many of us. So it's my great pleasure to introduce Justin Schirmann, from CNRS Grenoble, who will talk about geometry-enforced topological chiral fermions in amorphous chiral methods.
Hi, so good afternoon, everyone. Thank you for the introduction and for being here. As said, my name is Justin Schirmann. I'm a PhD student at the Institute in Grenoble in France. And I'm working in the group of adult evolution. And the work I'm going to present you today is about geometry-enforced topological chiral fermions in amorphous chiral metals. This work has been done also in collaboration with Benjamin Wheeler, who's now a researcher at CEA in Saclay. And so there are quite a lot of words in this title, and my aim during this talk is basically to walk you through all of them and make them like clear. So let's start with the one that appears twice in the title, which is chiral. What does it mean? Well, if you look at your hands, you have one left and one right, usually. I mean, if you have 2 hands, you have like more than the average number of hands in the winter. And if you look at the mirror image of your left hand in a mirror, you get your right hand. And those 2 objects are non-superimposable. And this is the reason why we say that they are actually chiral. Thing is, I'm a condensed matter physicist and not an orthopedic surgeon, so I don't really care about hands, but rather about crystals. And for example, we can observe also chirality in crystals such as tellurium. And so this is the right enantiomer and the right enantiomer. And they belong to different space groups, but we don't really care about this for the moment. Just to say that this also exists in the realm of condensed matter. So next, we will discuss a bit about topological, what we call chiral fermions. So what does it mean? What do we call chiral fermions? So our starting points during the talk and what I will focus on during the talk is this kind of things. So you have a linear dispersion relation. So this is momentum, this is energy. And in 3 dimensions, you can write the Hamiltonian describes the physics of this thing as basically H equal plus or minus K dot sigma, where sigma is the 3 vector containing the Pauling matrices. And so if you compute the eigenvalues of this Hamiltonian, you basically observe linear crossing. And this crossing precisely is what I call bifermion. Great. Thing is, when we deal with crystals, things are not that simple because on the previous slide, this was a continuous, what we call continuous model. But most of the time we deal with lattice model. And there is something a bit special about lattice model, is that the appearance, like this crossing that I just mentioned, comes always into pairs. Actually, the appearance of equally many right and left-handed species, meaning like the plus or the minus on the previous side, of valid particles with given quantum numbers is an unavoidable consequence of a lattice theory under some mild assumption. And one of the assumptions is that your lattice is invariant under translation. And this is a so-called Nielsen-Ninomiya theorem that appeared like first in the context of the weak interaction. When people try to put the weak interaction onto the lattice, they figure out that if you do so, you should have both left-handed and right-handed neutrinos. And we all know that this is quite a problem. So this is precisely what I was talking about 2 seconds ago. So imagine you have one biton, you should necessarily have another one. And the thing is, the way I understand this is that one bipoint is basically a source of Berry curvature, and the other one is a sink of Berry curvature. And all this lives on the torus. The other characteristic of the torus is 0, meaning that if you have like a source of vector field, you should have a sink of vector field somewhere else in the Brielle zone. And this is the way I understand why they come into pairs. Actually, of opposite chiralities, because one is a sink, the other is a source. So, how can we study this kind of thing? We start by introducing a simple 2x2 model, which lives in K-space. This is the so-called Condensed semi-metal model. It is on the space group 22. And basically, we can separate the Hamiltonian into two parts. One that is proportional to sigma naught, which is responsible for the shift in energy of the nodes. And one part, which is this VI sine ki sigma I part, which is actually very important because this term breaks all the mirror symmetry. Because if you take, like, for example, ks to minus kx, if Hamiltonian is not less than invariant for this transformation. And we put ourselves in a regime where all the VI are one order of magnitude stronger than the TI. So this means that we are in a strongly chiral regime. And then we can plot the band structure of this Hamiltonian along the given k path. And we observe that we have crossings at all the time reverse or invariant momenta. This is just a zoom along near the gamma point, and we see that we have actually this linear crossing that was like mentioning before. What I just said is that we have these V terms that correspond to the breaking of all the mirror symmetries, and this is actually very important because if I was to compute the charge of each of the Y points individually, then I will find this expression, and you see that the charge of each of the Y points is actually proportional to the CH, which is precisely the sign of the product of all the VI. So this means that if one of the VI is negative and the two others are positive, then I have what I would call a left-handed chirality, meaning that my monopole will have a charge -1. And if the product is positive, I will have a left-handed or right-handed, and this will influence the charge of the monopole. So the charge of the monopole and the structural chirality are really like linked to each other. And that's something really important to keep in mind. Here I represent the Fermions for the left enantiomer, and same thing for the left enantiomer. And this plot actually corresponds to what you will observe if you were to compute the spectral function along basically a circle that is circling around the gamma point. You see that in this case, you have two right moving modes, and in this case, you have two left moving modes. So right moving modes for right enantiomers, left moving modes for left enantiomers. And all this is not just fantasy. It has actually been observed experimentally. And these are some plots that I took from this very nice paper from Niels Schroeder. You can actually see that, so this is an Amorphous plot of some Fermions. And you see that you have these features that are winding in the opposite direction for the left enantiomer and the right enantiomer. This was just to motivate the fact that this actually exists and it's not just like theoretical fantasy. So enough of crystals. Now let's get amorphous. So there are a few questions like, why do we care about amorphous? What can we say about amorphous? And also, what maybe like the most positive thing is that at the very beginning of the talk, I say that points are basically crossings in momentum space. So what does it even mean to have amorphous chiral metal? Because we don't have a priori bands. So let's start with a bit of context. So we know that thanks to recent development in topological quantum chemistry, nearly half of the crystal displays topological features at the Fermi level. But we also know that crystals are not the only kind of materials you can find. And actually, there are way more amorphous materials than crystalline materials. And there is this very nice quote from Richard Zahlen saying that nearly all materials can be prepared as amorphous solids. So this is the reason why this region is so huge. And so the aim is to find a way to somehow enforce topology in these amorphous materials. And this is precisely what I'm going to discuss with you. Also, if you read the paper from Nielsen and Mia that I mentioned before, and you go toward the ends, you realize that they actually propose amorphous lattices as a way maybe to circumvent the theorem they just mentioned. And this is something we looked at, and this is also something I'm not going to talk about. So this was just for mentioning it. Right. So how do we model amorphous materials? So first thing first, we have to disorder the structure of the material. To do so, we consider like three different cases. One is what we call Gaussian disorder. So you start with a regular lattice, and then you start displacing all the sides using the Gaussian distribution. And you say that all the sides that are closer to each other than a certain distance or c will be like connected to each other. The other situation corresponds to this uniform disorder, where you just like throw points at random and you connect them the same way as I mentioned before. Or you can do something a bit different, and you have this fixed coordination disorder, where like the sides are now at random position, but you will keep a fixed coordination inside of the board. In this case, you have a 4-4 coordination for all the sides in the board. Why we do that? Because chemistry also sometimes imposes the coordination in your system. And so if we want to model a real system, it's important to take these kind of things into account. But for the rest of the talk, I will focus on the Gaussian disorder. Okay, so on top of Gaussian disorder, what we do is having some chiral domains. So in that case, we have region in the system where the structural chirality is different compared to the rest of the system. So in this island, for example, I will have left-handed chirality, and on the other part of the system, I will have right-handed chirality. And in addition of that, we also disorder the internal degree of freedom frame, because, as I say, so I haven't shown the model, so this will be like a bit more explicit in a few seconds. So, if you were to work with amorphous material, yeah, question.
Sorry, in this, like, is the chirality a geometric feature? Like, can we see that? Or?
So you can't really see it from there. It's just that you have the hoppings, and no one of the hopping, instead of being positive, will be negative. One of the hopping will have like a different sign compared to the other, right? Because I say that the structural chirality is given by the sign of the product of the 3V.
All right.
So one will be different, or like just the product of the 3 has a different sign. Okay. So we have to have a real space model for this thing, because there is no K space at real. So one way to write this model in the real space is this form. So you have this F prefactor that mimics the exponential decay of the hopping strength with the distance. And you have this C alpha plus C beta part, which is where chirality enters, because at each side you can define a number which will be either +1 or -1, if we assume that all the V's are positive. So this will give you like the chirality. And you see that if you're from one side of given chirality to one of other chirality, this part will disappear. But you will still have this steep contribution, which is basically the so-called Dressel. No, this one is the Dressel spin-off hopping, and this is just some S-like hoppings between two sides. Yeah, question. So what I said is that structural chirality is given by the sign of the product of the V, right? And so it means that if I have like one side of one given chirality, all the hoppings like going from this side will have one side, okay? And so if I have like two sides of opposite chirality, then you see that there is something incompatible, and then I say that the V part will just like vanish for this hopping between the sides of opposite chirality. Does it answer? Okay, great. And so you have this model. This is very cool. And the question is, what can we do with this model? And one of the main questions is there a crossing? Question is also, what does it mean to have a crossing? Because I said there is no K space. Well, turns out what we can do is actually define a moment to resolve density of space. You basically take your real space Green function and you sandwich it with the plane wave vectors, which are both well-defined objects. And you can compute this quantity for different value of energy and also different value of K. Just that K is not bounded anymore between -pi and pi, but between -infinity and +infinity. And you observe that you still have some kind of linear-like features which are crossing at K equals 0. And I won't say gamma point anymore because we don't have this point. And this is for increasing disorder. And what we observe is that this crossing actually survives, which is first observation. Then second one is maybe the Fermions also survive, which would be quite nice. Well, if we do the same thing, this time at a given energy, but for two different momenta, then what we observe is the following. We have this thing which corresponds to the gamma points, and we also have this arcs. So this means we have crossings and we have arcs for increasing disorder. So at some point, everything gets a bit sketchy. So I won't say that the arc survives the infinite amount of disorder, but if you go to some reasonable amount of disorder, they are still there.
The base manifold, now it runs from -infinity to infinity, but
yeah, the thing is, so if you go away from this momentum, everything starts to get like blurrier and blurrier because you have like some overlap. The features are like basically overlapping themselves. And so everything gets like sketchy when you go to larger momentum. Also, the thing is, when you do disorder, the only thing that really exists is this gamma point because you are at infinite wavelengths. And so you're not really sensitive to the details of the lattice. And if you go to large momentum, then you are at smaller and smaller wavelengths. And so you're like more and more sensitive to what's going on. And then the features just like disappear.
it's like having a boundary condition. Zero constant that increase.
Yeah, it's just that you can't see anything like after a certain value of K. And I think in this case, after like 3 or 4 pi, you just don't see anything anymore. Good. Then, okay, I just said we have this linear crossings. We have something that looks very like Fermions, but we want also to compute like some numbers. So one question is there something quantized in the system? To do this analysis to know whether or not there is something quantized, we don't introduce, because we use what's called the effective Hamiltonian. The starting point is to define this momentum, the momentum Green function, momentum result Green function that I mentioned. So this is just the real space Green function sandwiched with the plane waves, where n are the orbital degrees of freedom, in this case spin. And so you define the effective Hamiltonian as the inverse of this effective Green function plus the energy, which is the same as you plug here. And if you plot the spectrum of this effective Hamiltonian, you see that there is a very nice agreement between the spectrum of the effective Hamiltonian and the structure, the features that we see in the simulation of the spectral function. This means that we can like trust this object to be like a good description of the system we are dealing with. One of the first things we can compute is the so-called spin texture, which is defined as the imaginary part of the trace of this time the momentum resolved density, the momentum resolved Green function times sigma I, where sigma I are the Pauli matrices. And so the rows represent the x and y components of this object and the color of the z components. So we see that in the preceding case, we have a monopole at gamma and other monopole at each time reversal invariant momenta. And now, if we increase this order, what we see is that we still have a monopole at gamma. And in this model, in part, which is particularly important to notice, is that there is a one-to-one connection between the spin texture and the Berry curvature. So this means that in the preceding setting, one monopole of Berry curvature is one of the monopole of spin texture. And I said that monopole of spin texture apply in our context. So this means this might indicate at least that we have a monopole of Berry curvature at the center of the Brilliant zone, even though it's a bit like that use of notation to say Brilliant zone, but near k equals 0, we should have a monopole of Berry curvature. How can we be sure that this is actually a monopole of Berry curvature? The thing is, what we can compute is actually some Wilson loop. So by Wilson loop, what I mean is that you have some closed loops, and you start at one point, and you ask yourself, how the states like evolve when I propagate it along a closed path. These states will have your phase, and we plot this phase as an angle, which parameterizes which loop you are looking at, and so we make like all this the loop being forming like a shell, 3D sphere. And so this is the formula, but what we care about, what is important is the process. And as I say,
This looks like you do it.
yeah, yeah. That's a good question. So you should pay attention. Here I wrote P instead of K. This means that I'm working with the eigenvectors of the effective Hamiltonian this time, because as I shown you, you have this effective Hamiltonian, which spectrum reproduces the features of what we see in the simulation of the spectral function. And then we trust this object to be a good description of the system. And then you can diagonalize this Hamiltonian, obtain eigenvector. And
So is that already this is what
that's exactly what, that's a fair point. We are like disorder averaging the momentum resolved green function. And then we invert the disorder average green function to obtain the effective Hamiltonian. And then from this effective Hamiltonian, we compute the eigenvectors and use them to compute the Wilson loop.
So you are coming back to the torus. We are 3D torus.
So the thing is, there is no reason
That
why.
is what is concerning. It's like if you are changing the base manifold every time.
But
I mean, now this T is defined on the torus.
no, I mean, this way you can go from minus infinity to
But
plus
then what will be
infinity.
the case? So if it goes from minus infinity to infinity, you have another complete base. So you don't have one-to-one correspondence.
Why?
Because you start with, I mean, let's say you start with something that is transition invariant. The number of
Yeah.
gates is equal to the number of points
Yeah.
and so on.
I agree.
When you go to coding disorder, now you're saying, well, T can be anything from minus infinity to infinity. So
Yeah.
no points.
True. But the thing is that anyway, if you take like a large system, you will still like numerically able like to compute only for a finite set of points, right? And so the thing is, okay, you do this, and thing is usually this operator is like not so you will have some unitary like problem, and what you do is to do some singular value decomposition to make this operator unitary, and this takes this like correct the fact that your path is discrete momentum space, and so you don't really have like issues at this level. Okay, I have like a few more slides. Okay, so what I was saying is that you can compute the Wilson loop. And what we did in this slide is that we progressively increased the number of left-handed sides. And so what you see is that at the beginning, we have a winding number of +1, because we have mostly right-handed sides. And hence the charge of the monopole around which we are computing the Wilson loop is +1. And then some point, so this is 20% of left, 40% of left, 60% of left, Wilson loop flips because we have no more left sides than right sides, and 80% of left, still -1 winding number. So this means also that what matters in the system is this average chirality. And if you have like average chirality -1, then your system, then the node at gamma will behave as a -1 monopole. And if you have more average +1 chirality, then the monopole at gamma will behave as a +1. Yeah. Yeah, the thing is that this is a very fine-tuned point. And so if you have 50-50 and you look at infinite wavelengths, what you see is that on average you're 0. And so this also will restore one of the chiral symmetry, because as I said, so
you don't have a normalized case.
So if you're at 0, then you're at very fine-tuned points, and like pathological things will happen because you restore this. You basically like restore somehow this mirror symmetry on average, and then you will like maybe gap the vibe at this side. Okay, so I will just move to the left side. Question is, I shown you like a lot of results on linear crossing. Question is, can we enforce all the types of crossings? And the answer is actually yes, as long as you can preserve local chirality. And this is what I show you here. We have this linear crossing. This is the one that I discussed up to now. But you can also enforce quadratic crossings and even multiples. So this is actually very generic. And as long as you can impose chirality, you will be able like to enforce crossings at the center of the at k equals 0. And with this, I want to thank again my supervisor and Ben. And if you have more questions.
Okay. We had a few questions already, but there's time for a few more. Yeah.
The number of bands crossing at the k equals 0 is somehow by the coordination number in the lattice, or what determines how many bands you can cross in a?
What determines? So, thing is, in crystals, what determines the number of bands that are crossing at a single point, or the dimensional, or the dimension of the irreducible representation of the little group.
Yes.
So, if you consider the right space group and the right number of orbitals, then you can write your E-reps, calculate the dimension, and then find the number.
It's the same. It's the dimension.
Of the E-rep. Yeah, but this in this case, it would be like the dimension of the E-reps of the average little group, because since the thing is disordered, you have to average, and then you have average little groups. Yes.
What sort of information is there contained in the off-diagonal bits like that? If you looked at like the effect count, then you could, by sandwiching it between like P and P.
Yeah.
Did you look at P and P prime?
So we actually looked at it, and what we found is that so what we looked actually are the matrix elements of the Green's function at different momentum, and what we found is that the off-diagonal terms in P are actually orders of magnitude smaller than the same P elements, and so we just like discard them.
Very nice talk.
Thank you.
So it's actually last year, Philip had very beautiful work showing that the Green's function technique we believe to work for China for many, many years actually fails if there's strong interactions. So basically in strong codices, Philip showed that one can change the chain number from 0 to 1, whereas the single-hearted Green's function just shows no signature. So Charlie gap will be solved. So I'm wondering that for disordered system, do we know whether this Green's function technique necessarily captures the right chain number, or whether the situation Philip proposed for interacting system might actually also rise here, where Green's function and the chain number actually the deep part.
That's actually a good question. Answer is I don't know right now. Thing is,
Local tuning markers that the amorphous version where your Schirmann version is called the Fermions. Amorphous that is made a local tuning marker distributes different charge. So I think there's more of the connection with amorphous.
I see. But I think a real space that
Okay, I think we'd better move on now. So thank you again.